Okay, thanks, Said. Thanks, everyone, for joining my PhD defense. I'm Hanene. I will be presenting today motivation and background about deep learning for medical image reconstruction and analysis, and we'll delve into definition and challenge, and then we will go through my contribution in this PhD thesis. So, breast cancer screening, the most frequently diagnosed cancer among women, the second leading cause of cancer-related death, with about 2 million new cases of breast cancer diagnosis worldwide, is very important for early detection. Early detection is very important and crucial for improving the quality of life and cure rate for patients. X-ray mammography is the de facto screening technique. However, it comes with some harm, as in terms of it's relying on ionization radiation, and it has low sensitivity for young women or women with dense breast. Additionally, the time availability of mammography device is often problematic, leading to long waiting time. Diffuse optical tomography, which rely on non-invasive and non-ionizing non-invasive and non-modality imaging modality, leverage near-infrared light propagation through tissue to assess its optical property and identify abnormalities such as cancerous lesion. Like we see here, is different optical property. This new imaging modality is emerging as alternative for X-ray mammography, and it's seen increasing interest. When it comes in portable design, in terms of, it allows many advantages in terms of low cost, lower power budget, reduced complexity, as well as it enables critical diagnosis for underrepresented community. However, this comes with some challenge as well in terms of reduced measured signal quality and information loss. This also makes increased complexity for reconstruction and diagnosis tasks. Diffuse optical tomography measures the distribution of optical property as a function of absorption and scattering coefficient. These properties, like we see here, are closely correlated to physiological marker and allow assessment of tissue malignancy. In the therapeutic windows between about 700 and 900 nanometers is a minimal light absorption by tissue component, which allows sufficient penetration of light within the tissue. When light is beamed into a tissue, a photon can experience many alterations till it is either absorbed or scattered. We consider the scattered light, we measure the scattered light for tissue diagnosis. In this thesis, we aim to develop novel computational medical imaging and analysis approaches for screening breast cancer lesion. We aim to advance the state of the art of diffuse optical tomographic reconstruction and diagnosis by recovering the presence and characteristic of lesion, of breast cancer lesion, as well as predicting their malignancy. We do this in a critical limited probe design setting using deep learning-based methods. There's many challenges that we face during our study in terms of real data, real clinical or real patient data scarcity, where we have only few samples with limited ground truth over via other modality, with no object or pixel level ground truth. Portability of the probe design involve compromise in terms of signal quality. We have also imbalanced data set where we have more scan over healthy tissue versus the lesion part. This study requires real-time reconstruction as a clinician want to see results on a real-time setting, and it requires low computational complexity because of the portability of the probe. Unbiased accuracy is crucial for ultimate downstream task analysis objective. So to start, we propose a deep learning for biomedical image reconstruction. We do a survey here. This paper has been accepted in Artificial Intelligence Review 2021. So we did a thorough survey of 154 research papers of deep learning for biomedical image reconstruction. We filtered contribution according to their venue, technical novelty, and paradigm. Looking at the bar chart in the right-hand side, we can see that MRI and CT received the most attention. This is due basically to the widespread of the clinical usage and the availability of real data set that use it for training. The market increase in publication in biomedical image reconstruction is basically a market starting last couple of years, where we start to see increase of interest of deep learning-based approach starting 2016. To do for this aim, we provided a high-level schematics to elaborate on different in model design for existing paradigm, where we classified existing works basically into 4 categories. Pre-processing in image domain, where the aim is to use deep learning to recover full sampled data from subsampled data that can be used later using conventional methods for reconstruction. A post-processing paradigm use a few iterations of iterative methods or simple analytical approach, and then enhance results using deep learning. There is a move toward a direct or end-to-end direct estimation, or what we call end-to-end model, where we move directly from sensor domain data to reconstructed image, avoiding any conventional methods in between. And a recent round is road to task model, where we focus directly on the ultimate downstream task, skipping or only recovering for reconstruction and task. We highlight the pros and cons of each paradigm. We provided a comprehensive summary of existing algorithm split across informative dimension in terms of different input, model design, architecture, different classes, different performance metrics, and used benchmark dataset. We also analyzed it and identified challenge and open opportunity. So our next approach will delve into deep learning-based image reconstruction for diffuse optical tomography. This paper has been accepted in PKI Workshop 2018. So, given that there is no prior work leveraging deep learning for DOT image reconstruction, usually image analytical approach are used for fast but suboptimal solution that can be inaccurate sometimes. So we propose here to use deep learning for fast and more accurate, hopefully more accurate reconstruction. The challenge here would be how would we train the model given that deep learning requires a large amount of pair of data, and what architecture design should we adopt? So propose here the first end-to-end deep learning model for near-infrared based optical imaging, where we leverage a physics-based optical diffusion simulation to generate in silico training data. We evaluate our results on real measurement on physics phantom collected with our DoD probe. So to do this, we generated basically a set of mesh, and where we define different lesions in terms of different number, different size, and different penetration. And we fed this to a diffuse optical tomographic software, where we assign different optical property, and we mimic the probe designs in terms of different number of source, detector, boundary condition, and frequency used. We run the forward server to collect the measurement via this ground truth data, and we use these 2 pairs for training. We propose our proposed architecture. We propose here to optimize the parameter of a CNN convolution, of a CNN model in an end-to-end manner in order to learn the mapping between the in silico, the measurement, the collected measurement data and the ground truth image. To do this, we propose our architecture consists of a fully connected layer that map the measurement into a rough estimation that can be refined via a set of convolutional layers. We test our results on a phantom data set. So here we summarize our data set. We have in silico data set pair that we collected using our simulation software, and a test data set that include a solution, a physics-like solution that mimic the breast background, and a tumor-like solution also that mimic the lesion placed at a different location. We use the DOP probe, real DOP probe for measurement collection. Quantitative results on phantom data set show improvement in terms of localization error, but by about 50% in terms of lesion localization error, as well as improvement in terms of similarity, where we gain about 1 order of magnitude in terms of speed of reconstruction. Our next contribution, we will focus more on limited angle diffuse tomography. This paper has been accepted to PKI 2019. So far, we improved about 50% with respect to analytical methods, while we achieve in real-time reconstruction. So the aim here is, can we do better? Can we enhance the gap between in silico and real data set? So to do this, we propose novel similarity-wise laws to promote appearance similarity and penalize artifact, where we endorse the mean square error that we used previously with a fuzzy-Jacquard loss that assess the accuracy of the reconstruction with regard to the spatial relationship between foreground and background. We also use an adaptation modules that align the sensor domain distribution between the in silico and the real data set. We include here a multi-layer percentium to match the two distribution. Qualitative results in our network show improvement in terms of accuracy of lesion reconstruction, where simply by adding transfer learning, we see a reduction in terms of artifact. However, by adding transfer learning and fuzzy-Jacquard loss, we see significantly reduction in terms of artifact and lesion localization. So in our next contribution, we'll focus on multitask deep learning for jointly reconstruction and localization of lesion. This paper has been accepted in TMI 2021. So the main idea here is, can jointly solving for different tasks improve localization results? And how would our performance be in real clinical data set of the real patient? So we propose here the first multitask learning for diffuse optical tomography reconstruction and propose the first model that tests on real clinical data set. We leverage spatial attention mechanism in combination with distance transform-based loss function. We experiment on different network characteristic trade-off and prop design settings. So the main idea here is that we replace the residual network blocks by spatial attention-wise blocks to adaptively reweight feature according to their importance and then interdependence in future space by attending to the most important one in aim to improve model representation ability. We also introduce a distance transform loss to improve lesion localization, where we can compute the distance transform of predicted image versus reconstructed image, and we compute the L1 loss between them. This term has been added dynamically to the mean square error in order to improve refined results over time. We conduct experiment to assess network trade-off in terms of network characteristic, where we considered deeper versus shallower network in terms of layer, different number of channels, as well as sensitivity to localization versus reconstruction task. We also experiment in different probe design, where we reduce, given that we have only two sources, we reduce the number of the detector in the probe, where we try here, we aim to see the network performance as we have more sparse input, more with only few sample collecting the measurement. Quantitative results show the outperformance of our network, multitask network with respect when in contrast to analytical methods, iterative methods, as well as deep learning based methods, where multitask network improve lesion localization and reconstruction of optical property. So we tested our results here in a clinical data set with 2 patients where SWIP over lesion location and opposite healthy breast as baseline are collected. 5 measurements on average on each side are collected. So quantitative results show generalization of our results test to real data set where our model outperform iterative methods and deep learning based methods, especially in the healthy cases where we have less artifact compared to other approaches. The next target is orthogonal multi-frequency fusion based image reconstruction and diagnosis. This paper is still under review in GMI. So far we've been using only one frequency for reconstruction. In this paper, we leverage the multi-frequency aspect where different chromophore has different varying absorption property with different wavelengths. Combining multiple frequency can optimize signal penetration, reduce sensitivity to noise, and measure tissue response to light at various depths. provide information, and this can provide information about tissue composition. So to do this, we investigate the benefit of multi-frequency data on diffuse optical tomography, reconstruction, and diagnosis quality. An orthogonal multi-frequency fusion is adopted where in aim to maximize the interdependent contribution of each modulation frequency data and emphasize their collective strength using orthogonal projection laws. We also assess the direct medical prediction learning from signal and skipping reconstruction, where we learn directly from the sensor data the diagnosis. So in this architecture, we basically contrast a single frequency to a multi-frequency, where fitting only one frequency, we see reconstruction and prediction performance in contrast to a model where we use the joint representation from the different frequency for multispectral reconstruction and prediction. We also assess a direct prediction model where we skip reconstruction completely. So we adapt an attention-based mechanism to control the expressiveness of feature from each input, where we compute first an attention-weighted embedding given at each frequency, and then use Kronecker product to capture the interaction between the different frequencies. As a loss term, we use a loss that encompasses for all three tasks: reconstruction, lesion localization, and diagnosis, where the reconstruction path is basically our previous TMI paper with mean square error and lesion localization, while the diagnosis loss encompasses for cross-entropy loss and orthogonal projection loss that is used to maximize separability between classes by enforcing class-wise orthogonality in the intermediate feature space. We tested first our results on in silico dataset that mimic the prop design in terms of frequency and by creating a set of training and validation and test dataset. Evaluation results on synthetic dataset show successful exploit of different frequency, whereby contrasting multi-frequency model to a single frequency model, we see that improvement in terms of localization and different parameters, basically. And looking at qualitative results, we see improvement in terms of foreground versus background contrast when using multiple frequency. Looking at the row-to-task model, we see significant reduction in terms of computational complexity when the end task, when the model design is dedicated to the end task. Evaluation on diagnosis results show basically improvement when we use multi-frequency and clear dissemination between healthy versus lesion when are lumped regardless of their type. When we add multiple frequencies, so we have improvement of lesion, of healthy versus lesion. And when we enforce orthogonality, we see benefit of the feature space orthogonality when we use orthogonal projection loss. Performance gain, we see also performance gain with network capacity is dedicated to the end screen task. We also tested our results on a clinical data set with 9 patients where SPIP over lesion location and opposite healthy breasts are collected. We consider different patients with different tumor position, tumor size, and tumor type. Quantitative results again show improvement performance with multiple frequency with respect to only one frequency when used, where lesion is accurately reconstructed in most cases. However, healthy cases where only background is scanned, when only healthy tissue is scanned, highlight a better robustness of orthogonal fusion tumors, where we see less artifact where we have orthogonal fusion reconstruction. We also assessed our model performance when we vary the lesion size and depth. So we considered a scenario where we increase the lesion size and increase the depth. And as expected, we see reduction in performance as the lesion decrease in size and increase in depth. This is on par with the prop design limitation, where the penetration depth into breast is approximately half distance between the source and detector. So in summary, we developed a novel computational medical imaging and analysis approach for screening breast cancer lesion based on diffuse optical tomography. We use deep learning-based methods to tackle the problem of reconstructing and recovering the presence and characteristic of lesion, predicting their malignancy in a constrained limited imaging probe setting. We did this in real time. This is given a real-time requirement. We hope that this study improve the future line of care screening of breast cancer and provide them by providing unbiased accuracy and enable personalized medicine. As future direction, we can think about personalized medicine where the focus shifts toward tailoring healthcare to individual patient. This entails delving into temporal tracking, enabling us to monitor change over time, assessing prognosis, and predict treatment response. However, this requires a large data set, and this requires data set with the same patient over time. We can think also about synthesis of frequency and fusion, where the aim here is to examine the role of frequency, optimal number of frequency that can be used, but without having to prototype new design. We want to assess which frequency are better and explore the fusion technique with this synthesized frequency, and maybe adapting frequency selection for personalized medicine. Continual learning emerged as an essential paradigm as well, where adapting model and technique over time is crucial to keep in pace with evolving medical knowledge and new data flow. I would like to thank Professor Ghassan Hamarna for his invaluable advice, continuous support, and patience during my PhD, our collaborator for the insightful feedback, my lab mate in medical image analysis for their time that we spent together, and all my committee members for their time and feedback. Thanks all for your attention.